Good morning, all. Today we can discuss about the DAC ADC specifications. So, in last class we have studied the ADC and DAC. Actually, if your range is between analog value range is between 0 to 8 volts, it is divided into 8 equal intervals and the corresponding each value, that is 0 volt is equivalent to 0 and 1 volt is equivalent to 0 digital value, 2 is equivalent to 0 You can represent up to 7 volt, that is 1 LSB less than the actual full scale range. Yeah, if you're increasing or if you're reducing the step size or levels, of course, you need more number of bits for the digital representation. That means if you are taking 4 bits, then this same level can be divided into 15 levels or 16 levels. So what are the different specifications of ADC or DAC? First one is resolution. The resolution of a converter is the smallest change in voltage produced at the output or input of the converter. An 8-bit an 8-bit converter An 8-bit converter DAC has 2 raised to 8 minus 1, that is 255 equal intervals. While a 3-bit converter has a resolution of 1 by 7, that is 2 raised to 3 minus 1 part in resolution. So a resolution is the value of 1 LSB increment. This can be represented in 3 ways. One part in 2 raised to n minus 1 or 1 by 2 raised to n minus 1th part of full scale or a 3-bit or n-bit resolution. The second specification is linearity. The linearity of an ADC or DAC is the measure of its accuracy and tells how close the converter output is to the ideal characteristics. In an ideal DAC, equal increments of digital input gives equal increments of analog output and the characteristics should be linear. But in actual DAC, this is not possible. So here shows the linearity error of a 3-bit DAC. So if there is an increment from 00 to 001, it should change from 0 volt to 1 by 8th VFS. When it changes from 001 to 010, it should change from 1 by 8 VFS to 1/4 VFS. Likewise, it should increase. This line shows the ideal characteristics, while this curved one shows the actual one. That means here there is an increase in 001, there is after that there is a decrease in 010. So we have to calculate the linearity error in order to find the good correctness of the DAC or ADC. The linearity error is expressed as a fraction of LSB increment. If the error is less than plus or minus half LSB, of course we can consider it as a good converter, because if the error is in less than or greater in between half LSB, actually that will not affect the output. Next specification is offset error, often called zero scale error, indicates how well the actual transfer function matches with the ideal transfer function at the center point. For an ideal data converter, the first transition occurs between at 0.5 LSB or above. If the input changes from if the input is greater than 0.5 LSB, that is from 0, actually that we have to then it is there is an output change from 00 to 001. Similarly, for ADC, the zero scale voltage is applied at the analog input and is increased further for first transition occurs. That means, but with that offset error in actual case, if you are giving 0 volt for ADC, there might not be 000. And similarly, in the case of DAC, if the input word is 000, it should, for an ideal case, it should be equal to 0 volt, but in practical case, that might not be. So then we can say that there is an offset error for that particular converter. അതായത് 000 കൊടുത്തു കഴിഞ്ഞാൽ 0 volt കിട്ടണം ADCക്ക് അല്ല DACക്ക്. അതേപോലെ 0 volt അല്ലെങ്കിൽ 0.5 ലെസ് ദാൻ ആയിട്ടുള്ള ലെസ് ദാൻ ആയിട്ട് കൊടുത്തു കഴിഞ്ഞാൽ you will have to get 000 at the ADC output. എങ്കിൽ ഓഫ്സെറ്റ് എറർ എന്ന് പറയും. Gain error is how well the slope of actual transfer function matches with the slope of ideal transfer function. Gain error is usually expressed in LSB or a percentage of full scale range. The gain error is full scale error minus offset error. So actually here for the DAC, shows the gain error. So actual value, gain is the ideal value, but this is the this is the ideal value and this is the actual value. So this is the gain error, and here there is no offset error, but in actual case, if there is an offset error, that output may start somewhere here or here likewise. Okay. So gain error and offset error, which shows the how the ideal characteristics, the actual characteristics is different from the ideal characteristics. Here shows the for the case of ADC, the gain error, the ideal characteristics and this is the actual characteristics. Here the ideal value is the actual value. The difference between the actual value and the ideal value gives the gain error. Absolute accuracy is the maximum deviation from the actual converter and ideal converter output. So if you are considering the gain offset error and all any other error, if there what is the deviation from the actual converter and the ideal converter? Well, relative accuracy is the maximum deviation after gain and offset errors are removed. If you are not considering these two errors and while considering all other errors, what is the maximum deviation? That gives the relative accuracy. Monotonicity. A DAC is monotonic if the analog output always increases as the DAC code input increases. An ADC is monotonic if the digital output code always increases as the analog input increases. A converter has to be monotonic if the linearity error is not greater than plus or minus half LSB. That means in usual case, what we expect is when the output input increases, output also increases. But sometimes this is not possible in the case of DAC or ADC. Then we can say that DAC ADCO is not monotonic. Here say If when the input changes from 00 to 001 actual, there is an increase in actual value. But when it changes from 010 to 010, 001 to 010, there is a decrease in the actual value. But what we expect is that there is an increase in ideal or actual value. But the actual case, there is a decrease in the value. This shows that that particular DAC is not monotonic. And here also there is a decrease, that here again 101 to 110, there is a decrease in value, which shows that this DAC is not monotonic. It's the settling time, the time taken by the converter for the output to settle within a plus or minus half LSB of the final value following a call change at its input. That is, if there is any change in input, what's the time taken by the converter to settle the output at within plus or minus half LSB. Settling time is affected by the slew rate of the output amplifier and switching time of the logic circuitry due to the internal parasitic capacitance and inductance. That means actually the DAC or ADC is fabricated within an integrated circuit. Always there is internal parasitic capacitors and inductance which slows down the working of the integrated circuit. And also we all are realized with the op-amps, and as we know, studied earlier, the op-amp has a slow rate. That means some op-amp is having very faster rate to respond to the input changes. That means very small slow rate. But while some other op-amp is having a very large value of slow rate, means it will take more time to change the output when there is a corresponding change in input. So that affect also, that slow rate for the internal parasitic capacitance and inductance also affect the settling time of the output ADC or DSC. So these are the main specifications of ADC and DSC, that is resolution, linearity, linearity error, offset error, gain error, accuracy, monotonicity, setting time. So by this we have completed the 6th module. Any doubt?